Hello, I'm Grant Graydon. I'm here to do an example problem for you for solid mechanics. I'm the tutor for solid mechanics, and while no one is showing up for tutoring right now, I figured the next best thing I could do is provide further practice problems and examples and resources I found valuable when I took the class to try and help you guys through it. So that's what this YouTube series is. Still, you should feel free to come to tutoring if you want. Now let's get right into the practice problem here. So this is from an example problem from when I took the course, where we are given the shaft radius as well as what's going on here, and we're asked to find the max shear stress developed at cross-section AA. Now we're also told that these are free-rolling bearings, so we just negate any friction going on there that's causing torque. So the first thing we're going to want to do is just rewrite this with the free body diagram. So if we were to look at this, we've got one torque like that, another torque going like this, like this actually. So I'm going to personally consider counterclockwise to be positive when I do this. So our next step is simply to use the torsion formula here to figure out what's going on. Now, before we actually use this formula right here to figure out our shear stress, we're going to want to figure out how much torque is acting at AA, which is right over here. So we've got 12.5 kip inches, 30 kip inches, 42.5 kip inches. Now I'm going to sum the moments up at AA. So we're going to say it's at rest right now. You know, we've got these torques acting, but it's not moving. So I guess in the end we didn't even need to worry about that with the bearings. Now, because of this orientation, the 42.5 is positive, minus the 30, and then minus the torque acting. And then I'm going to say that this is all in kip inches. Now, why are we excluding the 12.5? We're excluding it because we are looking at our cross section here in this direction. Like, we've got our eye right here and we're looking at it from this way, so we're just going to negate the 12.5. But it's okay because the 12.5 will come out anyways here. So we're going to say 42.5 minus 30 minus t is equal to 0. We end up getting t is equal to 12.5. Kip inches, or kilopound inches. Now we can go ahead and use that formula from earlier. So 12.5 times 1,000 will give you pounds. pound-inches. And we're going to multiply that by the distance. In this case, it is just our radius, but what c is our distance away. So c is right there, which just so happens, because this is cylindrical, happens to be equal to r. So 12.5 times 1,000 times 0.75 inches divided by our polar moment of inertia, which happens to be, because we're once again working with a circular shape, our polar moment is pi over 2 r to the 4th, which happens to be 0.75 inches to the 4th. If we want to make our calculations easier, we can just cross that out and make that into a 3. So tau is equal to 12.5 times 1,000 divided by pi over 2 times 0.75 cubed. And then our units here are going to be, I believe, pounds per inch squared. Going ahead and calculating that now. We get that our shear stress is equal to 18,862.81 pounds per square inch. Or if we want to put that into KSI, we just divide by 1,000, and we find that tau is equal to 18.86281 KSI. And this problem is done, because that's what we were looking for. Thank you, and have a great day.